Hello, my name is Victoria Morris, and I'm an independent consultant working for Atrium Health. Atrium Health is the second largest not for profit health system in the US. The VA is the first. Today, we're going to be walking through a real world case study in migrating our genomic pipelines from a Bash Hive on HDI configuration to Spark and Azure Databricks on Microsoft. First, we'll do a quick overview of our data lake and some background on why we decided to move to Databricks. Then we're going to be talking about migrating our two genomic pipelines, talk about some things we learned, and end with the impact it had on the business. We value your feedback. Please don't forget to rate and review the sessions. So let's begin with link. Back in 2016, we were asked to solve this problem. Genomic reports are hidden deep in the EHR and scanned reports. We receive them from multiple vendors. They look different and are very long. It takes a lot of manual effort to summarize them. These reports make generic clinical trial recommendations, which may or may not be available at our oncology center, called the Levine Cancer Institute, or LCI. And these recommendations need to be translated into our specific available trials. Bottom line, it's complicated, time-consuming, and manual. The objective of the LCI Integrated Knowledge Base, or LINK, is to combine data across various data silos in the organization, a common use case for data lakes. Originally, we had 4 people. Then there's only Lance and I left. Lance's primary focus in this project is on infrastructure and negotiating with security to get data into the data lake and making sure we keep within budget. I focus on the algorithm that runs the back end, as well as developing the front-end user interfaces and any new functionality requests. Additionally, I keep the pipeline running smoothly day to day, troubleshooting any issues as they arise. As you can see, we have various data sources converging into our data lake in Azure. All of this data is transformed by algorithms into our 2 pipelines. Our first pipeline, clinical trials matching, actually begins in EA Pathways, our Fire Smart embedded app in the EHR used to ensure consistent care across patients regardless of treatment location by using approved pathways for treatment. Providers determine the best possible treatment pathway, which may include genomic testing. The clinical trials matching pipeline then takes the results from these 2 external tests as input, merges it with the other relevant data known about the patient across the data lake to generate clinical trials matching and genomic report summary. The second pipeline is for the pharmacogenomics. It starts from internal genomics testing results, where the raw 1 and 2 allele calls from the internal lab are transformed to the genotype and phenotype. They derive clinical recommendations and then generate a summary report. Here's a look at the original tools and the data flow that supported the 2016 process. We started agnostically with a bash script that used cron to control and run jobs, Scoop to gather data, Hive to do the algorithm. We used MS Web Apps to hold data on an in-the-cloud SQL Server backend that was auto-created by Microsoft, with a front-end user interface that was also auto-generated but was customizable. We used MS SharePoint Designer and PowerShell to move information between SharePoint lists and databases, etc. We're receiving a lot of different data formats: XML, comma-separated value files, PDFs, BAM, FASTQs. We pull full table copies from internal databases and from Netezza, our enterprise data warehouse. We pull queries across multiple tables or full table reads of data in the Azure storage using Scoop. Our pipeline went live in August of 2016, starting as a proof of concept. Over the years, there have been tweaks. Once Microsoft stopped supporting web apps, we were asked to use the new MS Power Apps. So Power Apps replaced web apps, and Flow, which was the original name for Power Automate, replaced SharePoint Designer and PowerShell. We added the additional labs inbound and more data formats, JSON and RSID files. We created Azure SQL Server databases to replace the auto-generated web app ones. And all that time, we continue to maintain a daily production run, multiple reports per day to support clinical users, and the weekly genomics tumor board. The Hive backend grew to over 8,000 lines by the time we migrated to Databricks. But like any great success, we had issues. With over 180 oncologists, plus pharmacists, nurses, residents, lab folks who use this data in real time to make clinical decisions on patient treatment options for real live people, when it stops working for any reason, it's a big deal. We were early adopters of HDI. Microsoft had not envisioned people just turning on and leaving these clusters up and running for years. In the cattle versus pets analogy, we were a bad cow named Fred. Safe mode kept killing us. Seemingly randomly, we'd get up in the morning and realize that everything had failed overnight with no error report and have to rerun hours of work after getting out of safe mode. We were crunching through a lot of data. 6 million patients, 12.5 million encounters per year times 5 years to find the right patient's record for the provider who ordered that test, just to pull in all the background information on the patient from several different systems before we even started looking at the results. I broke Visual Studio a couple of times before we were told to abandon Visual Studio and move to Visual Code. It was an expensive operation, as I was constantly being reminded, and we tried lots of things to pare down expenses, like scaling, which again, we managed to hit a hidden limit on. There was a max number of logs hidden in the design that no one expected you to reach. But after so many years of operation, lucky us. This scaling also introduced a lot of instability. We always had IP address issues, or rather lack of IP address issues. Scaling had a negative impact on that as well. We'd periodically lose IP addresses that were never released by the automated scaling down process. Eventually, we would run out of IP addresses and everything would fail. Next moves. We knew roughly what we wanted. We wanted value. We wanted to stay in the cloud. We wanted flexibility in programming language choice, and we were finally ready to commit to Microsoft. We needed a HIPAA-compliant infrastructure that was stable, self-sufficient, and did not require a lot of tinkering. I wanted something that would get me out of the Visual Studio, Visual Code world into something that was easier to use, like notebooks. We decided to move to Databricks to manipulate, clean, and gather the data together. We introduced data factories to move data around instead of using the command line. For myself, the tipping point was not having to hands-on manage the infrastructure anymore. I am not a hardware person, I'm a software person. Speaking of migration, start small. There is an enormously steep learning curve for Databricks, and not just because this pipeline requires me to be fluent in a lot of other technologies besides Databricks, like Power Apps, Data Factory, Power Automate, Power BI, and SharePoint. So we looked at starting with the second pipeline, which was much smaller, and it was much easier to start from scratch. Pharmacogenomics is that personalized medicine you keep hearing about, where depending on your genes, your body may react differently to medications. You might need a higher dose or should not be prescribed some medications at all. Driven by a Power App, this lets our internal lab generate lab results for pharmacogenomics to be translated into a report. At the 200,000-foot level, and if you are intimately familiar with genomics, please forgive my nickel-dime Torah explanation. Genomics testing slices up the double helix of your DNA, RNA, and numbers each piece, then lines the two double helixes back up, and you get a letter representing one of the 4 possible acids, A, T, C, or G, that is in each position, called allele call 1 and allele call 2. Combine a bunch of these SNP IDs, say 1, 2, and 5, and you make a gene. And depending on what letters are in call 1 and call 2, you have a genotype or variant. Wild types are normal, or maybe you're a star 6. These gene variants distinguish how your body will metabolize medications and or the efficacy of prescribing a medication to you. This is the RSID file we receive from the lab. We get the sample ID, the NCBI SNP reference number, the allele 1 and 2 calls, those CTG, and for some reason a dash. I don't know, maybe alien DNA. The truth is out there. Dun, dun, dun. We actually started this app with the lab sending us this spreadsheet, asking if we could create an app to read these files, the files from the previous screen, and translate these phenotypes from the lab results into a report using these Excel spreadsheets. This is the resulting Power App screen from that spreadsheet. The screen does the phenotyping based on the gene selected and the possible variant combinations. A metabolizer is assigned. This screen dynamically redraws depending on the number of variants. The lab defines all this themselves through other screens in the app. The lab users review the patient's results and ensure they match what they saw in the machine. They also add pertinent info that was not available in the raw data. This shot shows the gene CCYP219, which is made up from 3 RSIDs shown here. And these are the allele 1 and 2 calls for that specific patient. Once the lab is satisfied, they sign the results and they fall off their queue and it jumps to the clinical review team's queue. Here, the clinical interpretation work queue is presenting a patient for review. Staff can add a personalized consult note, edit text, preview the PDF report, sign off the results as complete, and then it drops off their queue. There's only one notebook for pharmacogenomics. This started from one of my first notebooks. I didn't know I liked Scala, so it's a Python notebook. No worries, I just change each cell as I go. One of the interesting technical challenges to make the proposed workflow for this application to work is that we needed to be able to run this notebook on demand from a button push inside the Power App, which is accomplished by a Power Automate called a data factory to run the notebook. Okay, back to our 8,000 lines of Hive code in pipeline. So we have 4 external labs sending us results, each one in its own format. This report is 15 pages long. I've edited it down, a bit abridged, if you will, and these potential clinical trial matches are what may or may not exist at LCI. And keeping in mind, I'm not sure how anyone not intimately familiar with genomics and all the clinical trials under ASCO could even begin to utilize this page. Or you can have this simple summary paragraph and eligible clinical trials paragraph 2. And yes, this is the actual result from that 15-page report. Clinical trials matching is incredibly difficult and requires an intensive manual effort. The physician going through the patient's record and looking up what is required for a variety of possible clinical trials that they may or may not be familiar with is prohibitively difficult. By automating this process, providing clinical decision support, we increase the ability of providers to match patients to clinical trials. Why is increasing clinical trial participation important? Well, aside from it being part of Atrium Health's 2020 goals, advances in care. Clinical trials are how we test and make changes to treatments that improve care and outcomes. Patients get care at a reduced cost, Atrium Health gets revenue for participating in a clinical trial, and physicians get prestige and recognition for getting their names associated with clinical trials. So it's a win-win-win. Being able to match clinical trials against these 10 criteria flexibly with no hard coding is a very non-trivial accomplishment. We've been looking at commercial matching products which have extremely limited numbers of genes and criteria, all hard-coded with about a 2-week development cycle for each individual clinical trial. Here at Atrium, we have a couple hundred clinical trials open at any given point in time, with lots of movement, opening and closing of trials daily at Atrium. We use Power Apps for staff to manage and maintain how they want things to be matched and what information should appear on the summary and how it should look. We try not to hard code anything into the algorithm wherever possible. It's all run from the features in these tables that they can manipulate in near real time. Any changes made today are part of tomorrow's run. No IAS intervention required, and what is hopefully a friendly, easy to use interface. These are complex relationships that we're trying to describe, and a large part of the redesign has been making it simpler and easier to enter the clinical trial data. A clinical trial has a parent record, a name and other relevant data like age range, status, gender, clinical trial criteria. Allow us to branch from multiple genes. A clinical trial may have one clinical trial criteria or many. Asker Taper has over 100, for example, but there are lots with just 1 or 2. Clinical trial criteria, the child record, has a gene to match the results against, normalized machine results. Then for each feature, like tumor site, we have 2 possible states. I want most things with only a few exceptions, include any except, like the orange tumor button, or I want a couple of things and I want to exclude most, which is what's happening in the green diagnosis button. Only include this short list. Button text changes, as well as the collections that are displayed below each button, which summarizes the choices made on other screens. Pushing a button navigates you to a new screen to define inclusion and exclusion criteria for that feature. For lab results, you need an operator like greater than, or less than, or equal to, and a value. And since we receive results from multiple labs, there may be differences in units of measure. Most are cosmetic, like this example, but you can be completely different scales of measurement, like decograms per liter versus micromoles per deciliter. So hemoglobin can be measured where a normal result is 120, or using the other scale, 12. Overall, You can use the red slider to define if you want to count at a match if you meet any of those lab results, or you can flip the switch and require all the labs to be considered. The large gray button changes the overall logic, which is currently only include these, that short list of include, but you could say include any except what I define here. This is the summary results template page. One of the most important aspects, once we have the correct data, was how it was displaying to the provider. Dr. Farnfar is extremely detail oriented, and that's what makes her great at her job. She can self-determine whether or not a result displays for each technology, right down to only for a specific gene on a specific technology for a specific result. She defines exactly the title and what variable she wants displayed in the details line. Again, no IIS intervention, this is all self-service. Any changes she makes are seen in tomorrow's run. In this example, any mutated pathogenic gene from a CLIN T7 technology should display. In Databricks, we'll substitute the number inside the angle brackets for actual values for the biomarker and NGS protein change when it calculates the summary. This one is for this specific gene, TMB, and only for this result low, only in this technology. Frame shifts are not important enough to display in the summary, so those results are removed from view. Display in the summary is independent of clinical trials matching. Once we finish clinical trials matching, we add to the bottom of the summary any results that would not normally be displayed in the summary, so it makes sense to the provider reading why there was a match. A good example is wild types. We do not display wild types in the summary unless they're used to match a clinical trial. The reports review allows for a curation of the results of the algorithm. Here you can open the original full PDF using the purple button. You can see the raw machine results in the table below that derived the summary. The orange buttons let you quickly move to another part of the app if you need to tweak something, like how it should be displaying or matching criteria. Using the two edit controls, you can manually override the results from the algorithm for this patient today. We periodically review the manual updates against the algorithm output to consistently improve the algorithm. So all that data, XML, CSV, JSON, data table reads, SQL pulls, feed into the data lake in Azure, where Databricks runs its notebooks. Reading in the features from the Azure SQL database tables that were edited by the user in the Power App, combining it with the data lake data, it generates the results. Uploading them to the data lake or the Azure SQL Server database, where the curator can review and release using the Power App. The Power Automate flow moves the documents around and updates the SharePoint list. Power BI reads the data from the SQL Server database and updates its views. Emails are sent to indicate there's work in queues or new reports for providers are available. All of this is the power of an interconnected ecosystem. Databricks on Azure with Office 365. The Great Migration. For Databricks, we've broken the work down into several independent notebooks. Each lab has a separate notebook that reads their specific input data, XML, CSV, JSON, and transforms it to a standard format for matching and summary creation. This allows us to run a lab's notebook independently, since the cadence and time of day we get data is different from each lab. Then there's a second notebook that does the matching for clinical trials, and a third one that does the summary. This split is because there's an optimal number of cells per notebook. When you go over 100, you get that poor performance warning. It just seems like a good logical break to split things here to minimize any rework or reloading of table data. The modular nature also makes troubleshooting so much easier than the 8,000 lines of Hive code. You'd have to let the whole script run through for everything. Trying to debug was torture. Now I can just rerun a logical group, say one lab and the main match to check on a change, or just the summary to check on an issue with a display template. I created the algorithm in Hive originally, so it was actually pretty easy to translate since we treated the Hive tables like data frames, but there were, of course, some differences. In Hive, I have to create a table definition, which gets stored in the database. In Databricks, I need to have a schema to read the data. There's no header in my comma-separated value data, and over time, data has changed. We're getting more fields in 2020 than we did in 2016, so I can't rely on any of the infer options. There's also a couple of extra steps to get things in a SQL kind of mood in Databricks. I have a separate line in Python to read the data into a data frame using the predefined schema. And then from Python, I save the data frame to a table. Then things started to look very similar. Often we were doing the transformations Things could just be copy and pasted, but it was also a chance to rethink some original choices and improve the algorithm by redoing some of the logic in the newer version. Databricks notebooks manage the clusters that have been attached to them. It has been a lifesaver. Clusters can scale worker nodes up and down based on workload. You predefine libraries to be attached to clusters that are used for your notebooks. I prefer to write in Scala, but I can switch languages in each cell. And although I try and stick to matrix manipulation wherever possible, as Lance says, sometimes you just need a loop. Databricks by the numbers. We use a premium workspace. We have about 110 terabytes of data, 2.3 million gene results times roughly 240 clinical trial criteria times 10 features per clinical trial each day, because we recalculate today's clinical trial matches for all patients every day since trials open and close and a patient's eligibility changes. And yes, even during COVID-19, we're still seeing roughly one new report a day. Things we learned. Azure Key Vaults, totally worth the time to set up, especially as you expand access into Databricks notebooks to multiple folks. You do not want all those credentials everywhere in plain text. It's important to save a copy of those final working detailed instructions though, as you only have to redo this when you create a whole net new workspace, which is not often, and you will forget. Speaking of creating a whole net new workspace, if you do this unexpectedly, you lose absolutely everything. I know, so old school and old fashioned, but save complete copies of what you're doing periodically offline. And yes, we had to generate new workspaces twice during this project. Working with complex, deep nested JSON and XML sucks. I mean, it looks great in all those cute little examples they give you, but most real world self-describing data is messy, where you may or may not have a node, which may or may not repeat, and you need to shove it all into that structured table to do anything with it. Cardinality to the rescue. I use that function all the time to see if there was any data inside those complex arrays, which may or may not contain data. Another handy function was concat with string. It lets you concatenate strings or arrays or a combination of the two into a string. So if you're not sure if you have one null or multi of results inside your data, because it's complex and messy like life, you can convert the unknown to a final string to have everything fit neatly into your structured table. I generally use a pipe separator so I can dig through if there are many entries after the fact. This was a hard-fought lesson. Databricks only reads block blobs. Any other blob types, it doesn't even see the directory. Data Factory is a great tool. We just didn't use it as much as we thought we would. I'm no expert, but I use these all the time. If you create a data frame in Python and suddenly need to use it in Scala, you can't see it unless you convert it. I use SQL to convert between Python and Scala, and I do a lot of work inside Spark SQL directly. We stopped scooping where the data sources were relatively small and did direct connections to tables as long as I was not impeding production. This worked well, and it's the middle scale of code snippet. But if you stop or run all or cancel command in the middle of writing out to a table using that, you hose it completely. You will need the bottom code snippet to fix it. This cleans up the file system to allow you to attempt to write the table again. Because of the modular nature of our design, I save the end results so I can transfer the transformations and calculations from one notebook into another. And then I use the refresh table feature to pull the latest true value version of the table, regardless of what is cached in the cluster. I love Parquet. We get so many speed gains from it. But if you're working with the real world data, you may end up with a null column definition, which Parquet hates. Early on, after the initial read of incoming unstructured data, I usually cast any numeric column to its true type, int, float, double, as part of a transformation to avoid getting all the way through the script and hitting a null typed column error from Parquet when I'm saving the final results to a table. Business impact, more stable, less money, fewer breakdowns, much easier to troubleshoot. Increases in volume are handled easily. We went from a 600 gene panel to a whole transcriptome reporting from one vendor without even blinking, and independence for the end users. I'd like to thank Dr. Ragavan, the founder of our feast. As the head of LCI, he provides funding, guidance, and regulatory approval for all the data collection as primary investigator. Our customers, Dr. Farnfarn, Nuri, and Jay. On the IAS side, this would not be possible without Chris Danzy, Lance, Scott, Andy, Andrea Boranich, Stephanie, Melanie, Stacy, Kelly Jones and his team, and all the data systems owners who let us access their data, and all the Microsoft support people who helped us push the edges. Databricks, and of course, thank you for your time and attention today. Are there any questions?